Welcome again. So in today's lecture we will be discussing about associated operation of SN axis. So in here we know that in SN axis or improper axis of rotation we perform Cn, which is perpendicular to sigma. This is an operation there. So let's take an example of S2. So we know that in S2 there is S21 which is equal to C21 and sigma, and in S22 this is equal to C22 and sigma 2 or sigma 1 from here. So we know that this is equal to identity, and this is equal to, we know that anything to power n, we know that Cn to power n is equal to identity. So here this value will become identity, and we also know that sigma of every even number is also identity, and C21 of sigma is equal to identity inversion. So these are the important note that we need to remember. Let's make a note here. So here C2 which is even, so it is also identity. So if we equate them, then it is also identity. So S2 is equal to identity. So this is the associated operation for these type of molecule. Let's take another example here. Just like in S3 we perform S21 which is equal to C21 and sigma 1. Here we know that is equal to identity. And let's perform the C22. So here C32, I mean this is C31, C32, and it is also the C31 which is equal to identity. So in this example there is C31 and sigma. So this is the associated final answer of this. And if we talk about C32, then in here we can write this at C32 dot E. Why E? Because here a sigma. So we know that this value will become identity. So C32 is the final answer for S32 operation. Let's talk about the S33. So here C33 is present and a sigma 3 is present. So according to the note of the previous that I told you, that Cn to the power n, so in this case C3 to the power 3 is equal to identity. So this will become identity, and we can write this sigma 2 into sigma as the sigma 3. So identity, and we know that this will be even, sigma to power even is also identity and a sigma. So the final answer will be sigma. Let's discuss a question which is asked in the previous year in CSIR net. So here we need to tell about whether this is equivalent to what out of these four. So let's perform this C36. So we know that it is equal to C36 perpendicular to sigma 6. So we know that C33, we can divide this at C33 into C33. So as we all know that if these powers are same, when the bases are same, power will be added. So this will be like that, and we know that this is equal to identity because this is even. Sigma to power anything even is equal to identity, so this will become identity. So we know that the Cn to power n is also identity, so this all will become identity into identity, not identity. So answer will be identity. So this will be the right answer. Now let's get straight to the main point. What is a point group? So point group is the collection of all the symmetry operations corresponding to different symmetry elements shown by the molecule. So point group is the collection of all the symmetry elements, just like all the symmetry elements such as identity or the perpendicular C2 or S2 or sigma V's or sigma H's, all are present, which give information about the molecule. So for calculating the point group of any molecule, we follow this chart, according to which, if let's take an example of HCN, we know that the structure of HCN is H, single bond, C and N. So this is the structure of HCN. So to calculate this HCN molecule, we first need to check whether this molecule is a linear or not, according to this chart. So this is a linear molecule because it's present in single plane. So yes, it is a linear molecule, so we go to the left side and let's check whether it have an inversion or not. So we know that how do we check inversion. So first let's check, go from left, it is hydrogen, and let's go here, it is nitrogen. Not the same, it do not give equivalent structure, so this is not, inversion is present. So let's go to the N side. So this will be the point group sigma C infinity V. This will be the point group of HCN. Now let's take another example of CO2. So we know this is the structure of CO2. So here let's check, go the same thing with the molecule here in the chart. So it is a linear molecule. Yes, it is linear. Yes, it is linear. Whether inversion is present or not, yes, it have inversion is present. How do we check? This here oxygen and here oxygen, so same molecule are present, so inversion is present. So according to this, if we go from molecule linear, yes, inversion, yes, then D infinity H will be the point group of CO2. Now let's discuss another example, which is SF6. So to calculate the point group of SF6, we first draw its structure, a tetrahedral structure, and we know that it is linear, so it is not linear structure. So in the point group chart, we will move from here to here. So let's check the second step, the principal axis or two and more CN axis or not. So yes, there is one principal axis C4 and three C4s axes are present, so it is true. So we go Y. Then let's check whether this has inversion or not. So yes, it have inversion is present. So inversion is present, so we will go, let's check, is there any C5 are present. So no, there is no C5 are present, so it is octahedral. So the point group of this SF6 molecule is octahedral. Let's take another example of water. So we know that it is not a linear structure and there is no principal or CN axis, more than 1 2 CN axis are present, so it is not present. So we will go from here, if 2 or more CNs are not present and n is greater than 2, so we will move from no. Then let's check CN. Yes, it has CN axis, C2 is present, so yes, CN axis is present. Then we will check whether the now let's the next, yes, CN axis is present. Then we check the CN with the highest n, then is NC2 is perpendicular to CN. So if it is present or not, so it is not present. Then next step is to check, if it is not present, then we will check it has sigma D, sigma H or sigma V. So according to this, we do not have sigma H, there is no horizontal plane present here, and we have vertical plane, so the point group is CNV point group for the H2O molecule. As you can see from the next example, BF3 point group is D3H, so it is not linear. Principal CN principal axis are 2 and more principal axes cannot be formed. So Cn axis is present here, the C3 is present, and principal axis is present. So there are one C3 and three C2s are present, which is perpendicular to this. So it is present here, and sigma h, a horizontal plane, is present. A C3 is passing through the middle, and a horizontal plane will cut all the fluorines. So D and H will be the point group. As you can see from here, D and H will be the point group. This will be the point group. A sigma h is present here, and there are three C2s perpendicular to. There are three C2 perpendicular to, three C3 perpendicular to. So there are C3 perpendicular to three C2s. So as you can see, there is nodes NH3 molecule. So it has C3V point group. We can check that from the table also. And in next example, a CH4Cl molecule, a CH3Cl molecule, it has C3V point group, and a platinum group of propyl. So this is the structure of propyne, a triple bond carbon and a hydrogen and carbon, and these groups are attached. So here it is not a linear structure and inversion is not present. So this cannot be sigma D. Its structure is just like ammonia. So C3V point group is present here. So just ignore this. This is totally wrong. It is just like the structure, just like ammonia. So the ammonia which we see here, NH3, this will be the same point group, C3V. Now the next question which is asked in that is 2013 June, is that the principal axis here is, so we can just ignore this 3 because there is no C3 axis present in this molecule. So we can cut this option, and there is no D4 or C4 is present, so this is also cut. So D2 will be the only option in which this symmetrical structure is found. So N is equal to 2 is present in D2H molecule, so this will be the right answer. Now there is another example, very important example, which is of allene. And we know that the structure of allene is C double bond C double bond C, and one group is hydrogen just like that, and another group of hydrogen is just like that, and this will be in the plane. So this is the structure of allene. So we want to know about the point group of this is 2. So let's check whether this is a linear or not. So it is not linear, so we go to the N side of the chart. Then we check if any principal axis is more than 1 or 2. So no, there is no principal axis more than 1 and 2, so we go to the N side. And let's check whether it is Cn axis or not. So yes, it has a Cn axis, or C2 is present here. So, and let's check whether the NC2 perpendicular to C2 is, so this is also 0. And the fifth, let's check whether it has a sigma horizontal plane or not. So it do not have the horizontal plane, but it has a vertical plane or a dihedral plane. So sigma D is present. So D and D is the point group of this molecule. So this is also an important question asked in 2016 June net, CSIR net. So the question is the symmetric point group of most stable geometry of this molecule. So this molecule has one hydrogen here, a carbon and a chlorine, and this carbon and this carbon above the plane chlorine and below the plane hydrogen. So it's a trans structure, which is the most stable structure of these. So there is no chiral, so it is a chiral molecule, so there is no plane is present. So here plane is given, and C1 is not, C2 is also present here, so C2 will be the right answer. It is also an example in which N2F2 has two isomers. Which of the following is correct according to this question? Both has sigma V plane, so both have sigma H plane. So one has sigma H and one has sigma D plane, sigma V or sigma H plane, और none of them have sigma H plane. So कौन सा बोल रहा है कि which of the statement is correct? So according to this molecule N2F2, there is two possible geometry or isomers are present. One is cis and another one is trans. So in trans molecule, a horizontal plane is present because a C2 is going from here to back. A C2 is present here, and this will reflect, this will go here, this will come here, come back to the same position. So a C2 and a horizontal plane, if we cut this from this to this, of all the four molecules, all the four atoms will be cut in half. So a horizontal plane is present in trans, and a vertical plane which is present in here, C2, a vertical plane which will cut all these, which will reflect these molecule in the same direction. So C option will be the right one here. And this is also an important example, the point group of naphthalene. So this is the structure of naphthalene, and we can see a C2 is going from middle, and a C2 from here, and a C2 from here. So this is not a linear structure, and Cn perpendicular to NC2. So there is one C2 which is perpendicular to these C2s. So this is also present here, and which is C2 is perpendicular to two C2s. This will be happening in this naphthalene molecule, and we know that it has a sigma H, a horizontal plane which is passing from this molecule, and if we put a plane from this direction, so a plane is also present. So the final point group will be D2H point group present in the naphthalene molecule. It is important to note that a CCl4 molecule has, which is a tetrahedral structure, has a 4 C3s and 3 C2s. It is very difficult to understand, but this is the final result.